Now, following our other speakers, we asked her to provide 2 truths and a lie, and we will see if the audience can go all in and go 4 for 4. If so, I don't know, what should happen? I will pay off all your student loans, yes. All right, so the 2 truths and the lie, she provided 3 facts. One of them is she has been to North Korea. The second fact is she has met Neil deGrasse Tyson. The third fact is that she wrote a thesis arguing that the multiverse is complete nonsense. So, here we go. Through applause and general noise making, how many of you think item 1 is the lie? All right. How many of you think number 2 is the lie? Yeah, he is hard to peg down. How about number 3? Zili?
Number 3 is wrong. So I actually argued that the multiverse is a viable scientific theory, and there are ways to test it in my thesis.
The audience is 4 for 4. So, you met Neil deGrasse Tyson. What was that like? How did you meet him? How? I've sent him many emails. He will not respond.
Okay. I met him in the Columbia Astronomy grad student visit. There were like 20 of us. We all got into the Columbia Astronomy program, and they invited all of us to New York City to see their campus, and they planned for us a tour of the American Museum of Natural History, and he wasn't even on the schedule. When we got there, they just told us, oh, you can meet Neil if you want to.
No, that's nice, yeah. Everyone, let's give a round of applause for Zili Shen.
All right, so I am going to talk to you about the sun, and this is a project that I did last summer in Germany. So that's the institute that I was at. I'm not actually from there. I'm from UT Austin, as you probably know. So the sun, it's the closest star to us, and it is arguably the only star that you can observe during the day. So hence my warning, do not actually look at it during the day. Even though I hope my talk sparks your interest in solar observational astrophysics, please don't do it with your eyes. No matter what season it is, what time of the day it is, don't do it. Not with sunglasses on, not through a telescope. Just don't. But you see the sun every day, all the time, and I would argue that one of the most fundamental questions that you can ask is, what is our place in the grand scheme of things? And this question has been asked a long time ago. And this is Aristotle's answer, which is, we are right in the middle of it. Because, of course, humans are at the center of the universe. Where else would we be? So this is his idea of what the universe is like. Earth is in the center, and then you have some celestial spheres that are outside of the Earth, and the closest one is the moon, and then you have Mercury, Venus, the sun, which is the fourth one. And so he thought that all the celestial bodies are basically perfect, and they never change. But then he had to account for the fact that the sun puts out heat to the Earth, and you can feel rays coming from the sun heating your body up when you stand outside. So he said that the energy of the sun comes from friction. It's the friction when the sun moves on the celestial sphere. It moves fast enough that it generates some heat through friction, and we are close enough to the sun to actually feel the heat. So this was the view that people had for a long time until, like many other ideas that Aristotle had, this was proved wrong by Galileo. So in the 17th century, Galileo pointed his telescope at the sun, and by the way, he did not look through that telescope directly with his eye. Even though he did go blind eventually in his 70s, it wasn't because he looked directly at the sun. If he did that, he would have gone blind a lot faster. He actually had a safe viewing method, which is you project the light onto another surface and look at that surface. But anyway, he saw sunspots on the disk of the sun. And so this is a drawing that Galileo made. And you can clearly see these things are the things that make the sun less than perfect. And now we know that sunspots are actually cooler regions. They're cooler than their surrounding. And so the entire sun is a hot ball of plasma. And when you have a cool region like that, it doesn't shine as brightly as the regions around it, so it looks dark. And it's cooler because of how the magnetic field on the sun is arranged. But this is the knowledge that we have. Galileo didn't know that. Galileo only knew that this contradicts Aristotle's claim that the sun is perfect, because these things aren't perfect, and they also change over time. So people put a lot of their time into tracking sunspots. If you plot what you see, like for this sunspot, you plot what you see today and you plot what you see tomorrow, and you draw it each day on the same disk, then you can sort of find its trajectory. And you can see that all the sunspots move the same way across the solar disk. So people thought, well, maybe they're not actually moving, you just see them moving because the sun is rotating. So that's how people in the 17th century knew that the sun was rotating. And furthermore, they knew that the sun was rotating at different speeds, at different latitudes. So the sunspots move across the equator much faster than they move across the higher latitude regions. So this is what provoked the idea of a differential rotation, which just means that the sun rotates faster at the equator than it does at the poles. The sun is not a solid ball that rotates all at once. It's a giant ball of plasma. And so the plasma around the equator is going faster. And if you had a bridge from the North Pole to the equator, it will actually get stretched longer because the equator is going faster. So then you might think, people in the 17th century made these drawings. They are probably not very good. They're just qualitative, hand-drawn pen and paper drawings. But now we can compare them to a modern satellite image of the sun. So, you can't see it at the top. This is from the Solar Dynamics Observatory, or SDO for short. And by the way, if you really have the urge to find out what the sun looks like, instead of looking at it, you can just Google SDO and look at the real-time image that this satellite takes, and you can even do it at night. So this is a much better alternative than naked eye viewing of the sun. But basically, my point is just that the drawings of sunspots compared to a modern camera on a space satellite, they really look very similar. And so the historical records are amazingly accurate. And I'm going to show you another one with even more detail. So if I didn't tell you, you probably can't really know for sure that this is a drawing, and this is a picture taken from a high-resolution solar telescope. This is 1870s, this is 2014. And people have even captured very detailed morphology in groups of sunspots. So a lot of the pen and paper drawings were stored in archives. There's a huge archive in the Royal Astronomical Society in London. There are also a lot of archives in Germany. And this Astronomische Nachrichten, this is the German journal called Astronomical Notes, and this is where a lot of solar sunspot drawings were published. And also, just a side note, this is where I eventually published my recent paper. And I just find it very intriguing that my paper was published in the same journal as these hand-drawn drawings. I wish it was that simple for me. Like, if I could have drawn this and published it, that would have saved me a lot of time. But So now we're going to remember what you see here and compare this to what a telescope can see in the photosphere of the sun. So this is where most of the light is coming from. And you can see that there's a dark spot. It's smaller than most sunspots, but it's actually captured in this drawing. And so the level of detail in these drawings is quite astonishing to me. So now that we know that people with good eyesight and good telescopes have made good drawings, but what is this actually good for? Like, can you actually do any science with it? And the answer is yes. So you might have thought that this is just quantitative drawings of sunspots, but each of these people have devoted pretty much their entire lives to drawing sunspots. They make drawings every day. It's very typical to have one person making like 1,500 solar sunspot drawings over his lifetime. And so if you compile the records throughout his lifetime, you can actually find a lot of trends in these drawings. So this top plot is showing you the latitude that each sunspot appeared as a function of time. So when you go to the right-hand side, you are progressing in time. And from this is called the butterfly diagram, and it's a very famous diagram in solar physics because you clearly see that there's a periodicity. There's a pattern that repeats itself, and the period is roughly 22 years. So 22 years is the activity cycle of the sun. And these are drawings from 1860 to 1886. So the point was that because the solar cycle is 22 years, you really need long timeline observations in order to make a plot like this. And then on this bottom plot, it's just showing you the number of sunspots per year. And so you can also see that there is a cycle in these. And then if you compile all of the observations that you find about sunspots from 1600s all the way to modern times, you can actually find some very interesting trends here. So this is a German solar physicist who first noticed that there's a blank spot here, and this is called the Maunder minimum. And in the entire field of solar physics, there's a lot of debate over whether this lack of observed sunspots is because of a lack of sunspots or a lack of observations. I am not going to make any conjectures here, but I'm just mentioning it because this German physicist, whose name I will not butcher, he actually worked at the institute that I was at last summer. So it's the Liveness Institute of Astrophysics in Potsdam. It's in Germany, it's near Berlin. And I didn't know it at the time, but it turns out that this institute has a lot of history and has been a very important place for solar physics. It was founded in 1700 as the Berlin Observatory. But since then, a lot of physicists and astrophysicists have worked there. And they have kept on observing the sun. But now we have modern technology, we have cameras, we have better telescopes. You might think that we have to do better than pen and paper drawings, right? So there came my summer project. We have this small telescope. I have a picture of it here, but the actual mirror is only 10 centimeters in diameter. So it's a lot smaller than a lot of the telescopes you might have heard of. But this is enough for us to observe the sun. This is a good telescope because it's automatic, so we don't have to make a pen and paper drawing every day. This will take us a picture of the sun every 3 minutes as long as it is during the day and as long as the weather allows. And it also gives us pictures in 3 wavelengths. And in each of the wavelengths, you can see basically a different slice of information about the sun. They all tell you different things. And my summer project was to make these images precise enough for scientific work. So we want to find out not just qualitatively, how does the sun look, how many sunspots can you see? We want to find out what is actually in the data, and we want to find things like velocities. We want to accurately find where the sunspots are and where other weird phenomena happen. So I developed a method to clean up the images. So the bright points here and the dark patch there, that's not actually on the sun. This is just instrument artifacts due to the telescope. And so I developed a method to remove it, and I'm giving you a before and after comparison of what my method does to clean up our data. And after you clean it up, you can actually get nice things like this Doppler map of the sun. So I'm assuming you guys know what Doppler maps are, but I'm just going to tell you that the red means it's moving away from us, and blue means it's moving towards us. And the color indirectly represents the velocity. So the darker the color, the faster it's moving away from us, or in this case, towards us. And I'm also going to show you a movie that I made. This is just images captured during one day, and I put them all together into this movie. So the bright points are where there's a lot of energy and there are explosions called flares happening. The dark spots are sunspots. There's one here, there's one here. And then what my group was interested in studying were these cloud-like things. They're called filaments down here. And so with this 10-centimeter aperture telescope, you can actually see a lot of detail. And with this timeline of observations, you can see how it changes even during one day. And we have 6 years of data. So remembering what you saw in this movie, I'm not going to read you a quote, which says, this is about sunspots. Like clouds, they appear, divide, dissipate, disappear. In successive days, they will grow, others rarefy and vanish before reaching the extreme margin. So last summer, I made hundreds of movies like that, and I watched all the sunspots grow and rotate across the solar disk, and I thought this was a pretty accurate description of what I'm seeing. But this quote comes from Kepler of Kepler's laws, who worked out how planets orbit the sun, and he said this in 1613. So to me, this is very amazing that we are seeing the same phenomena as people in the 17th century. And to me, that's what's amazing about solar physics and about all of astronomy, because we see the same sun and we see the same stars. And when I worked at the Institute, I felt like I was part of this long and rich intellectual tradition of investigating the sun. We observe the sun and formulate theories to explain these observations. And as the observations get better, you develop more and more detailed theories. This is how a lot of scientists started to understand how stars operate. And so this is really what's beautiful to me, is the whole story. So even though in Austin it might be hard to go stargazing at night because you can't see the Milky Way due to the city lights, but you can stargaze at noon. So tomorrow, when the sun rises, you can go out, not with your eyes. Don't look at the sun with your eyes, but you can go out into the sunshine and feel like you are connected to something bigger. And that's what I want to leave you with.
Thank you, Zili. I have a very enthusiastic hand right in the front. Go ahead.
So you look like that video competition was in 2013.
Yeah.
So I think I read that NASA thought that the solar peak was maybe around 2011 for solar activity, but it's been increasing since. Mm-hmm. So where are we really in the solar cycle for
right now? Okay. So the question is, This movie that I showed you guys is from 2012, and the actual maximum of the last, or the current solar cycle occurred in 2011. So the question is, where are we right now in terms of solar activity? And right now, the sun is very quiet. We are, okay, I'm gonna go back to this butterfly diagram. So even though this is from like the 1800s, all the butterfly diagrams look like this. So we are in the part with like basically no sunspots. So you can Google Solar Dynamic Observatory or just go to the NASA website that has the real-time images, and you will see that there hasn't been a lot of sunspots recently. And similarly, the cool explosions that I showed you, like they're not happening on the sun right now because we are right now at a quieter part of the cycle in the sun. So that's actually a good thing for space weather, because whenever you have explosions like that, the energetic particles come out and affect satellite, and they affect communications. So now it's the more stable part in the cycle.
All right, so we also got an Instagram question, you guys.
Nice.
So to whoever that was, you can have 2 keychains. Also, we are 12 followers away from 300. Hook us up. Okay, so anyway, our Instagram question is, the sun is hot, so why are there cold spots on the sun?
Oh, that's a good question. Okay, so this is about sunspots. I don't actually have a slide that explains that, but let me just go to a sunspot. Basically, the sun manufactures energy in like deep in the center, right, where nuclear fusion is going on. But we see more or less the surface of the sun. So this is showing the photosphere, which is a layer in the solar atmosphere that emits most of the light. And this layer is it basically has plasma that's moving, and these plasma are charged particles, so they're constrained by a magnetic field. They can't just go wherever they want to go. They feel the magnetic force acting on them. And so whenever the magnetic field, there are field lines rising from below the photosphere, and whenever the magnetic field lines rise up, it basically changes the convection pattern and makes energy makes energy go up slower, so that these regions are cooler than their surroundings.
So it's relatively cold.
It's relatively cold. It's not actually cold. If you
still don't want to go there.
You still don't want to go there.
Yeah.
You mentioned your method for making the artifacts in the pictures. How exactly is that?
Okay, so this question is about how exactly my method works to remove the image artifacts. So basically, it's sort of a fitting and dividing kind of thing. So we can characterize what the bright parts and the dark parts look like by fitting a series of. Okay, so I guess it's kind of hard to explain this to a public audience, but
Is there math involved?
yeah, there's math involved. So it's math, but basically, you can think of any pattern on a disk as composed of the addition of a lot of like more fundamental things, like the lowest order you can go is just uniform, and then higher order things will be like bright here, dark here. I basically decompose the image into more fundamental parts and then remove the large scale variations while keeping the small scale variations. And that's how I get rid of image artifacts.
Up top.
So, can you bring back that chart where you had time on the x-axis and luminosity on the right? Yeah, that one.
This one?
Yes.
Okay.
Can you explain where was the data? I mean, how did you collect that data know the data is 1850 and 1700?
Okay.
Is that based on light year travel, or how do you know that data is correct?
Oh, okay. Okay, so the question is about how we collect and analyze like historical observations and how we know it's accurate. So first of all, the sun is 8 light minutes away. So when light leaves the sun and reaches the earth, it takes 8 minutes. So it's actually not going to, like the light travel time itself is not going to cause a significant delay. And you're right that people don't really, you can argue whether you can trust the year tags. Like you can take one of these drawings and it says like 1750, but how much do you trust that? Or if this one person kept making drawings and he just didn't put a date on it, like how would you interpret the data that way? So a lot of these drawings, like I mentioned before, they're hosted in some kind of archive, like in the Royal Astronomical Society or in the Liveness Institute of Astrophysics. So the ones that are actually used by scientists are the better documented ones. Like they select the ones they think are more trustworthy, and if it's just one stray drawing of a sunspot, then we don't know what to make of it. But basically, you need some kind of systematic thing to make you trust that observation. And so this is kind of like doing history research more than astronomy research. So excuse me for like not being an expert in historical methods. I don't actually know what makes them think some ones are more reliable than the others, but there's some sort of selection going on.
All right, last question right here.
Question.
All right, I seem to recall some correlation between sunspot activity and how much thermal energy is coming from the sun or reaching Earth. I was curious how significant that is, and something that you need to take into account when you're trying to have a climate change, or it's too trivial. Or what.
Right, okay. So the question was about whether the solar cycle has an impact on the thermal energy that gets to the Earth and whether that has any significant impact on climate or like the Earth in general. So I can say that the clearer links that physicists know about is that when there's more activity on the sun, there's more like solar wind and high energy charged particles coming from the sun, because they, like in the movie, there was like a bright flash on the sun, and when that happens, basically a lot of the particles get blown away from the sun, and some of those will travel, they all travel out, and some of those will get to the Earth. And so when they get close, they might hit your satellites, they might hit like the magnetic field of the Earth, and then they get funneled into the poles and you see aurora. So that's like a very clear link of how solar activity can impact our lives. There are times when solar activity is so severe that it's called a solar storm, and this can actually cause satellite communication to fail. And so this could significantly impact our lives. And there, like NASA has a lot of people studying space weather because of that. And then for the larger scale, the thermal energy output of the sun is pretty stable. The sunspots don't actually significantly impact the total luminosity or like the energy output per time of the sun. But there seemed to be some correlation between these minima and global climate, although there's not a definite explanation on how that works, so we're unsure on that end. And also, these two minima are not occurring during like one solar cycle. So this is like one solar cycle. These things are occurring over many cycles. So something is regulating a broader trend. On top of the 22-year cycle, you also see like this longer-term trend, and I don't really know what is behind that.
All right, let's thank our speaker.